Whenever you're ready, go ahead.
All right, Tracy, thank you. First off, I'd like to introduce myself. My name is Brian Schmidt. I work for a company called Mojave. Um, we have been manufacturing since 2022, but this is not new technology. We have applied it in a very new way, so it's very innovative. But liquid desiccant itself is not a necessarily new technology. So today I'm going to be going through how our product is different than what you might have seen before, and also how it's configured. Not going to be getting too deep into, the necessarily the configurations of the product or, what it looks like, what it weighs, anything like that. Really much more just about the technology itself. So Mojave is a manufacturer of innovative liquid desiccant systems. The company is introducing a patented technology that combines cooling, heating, and dehumidification into a simple, easy to install package. Our aim is to revolutionize the commercial air conditioning industry by providing the world's most efficient DOAS product. I'm sure many of you on this webinar know that a DOAS system is an energy hog, probably one of the biggest energy consumers of an HVAC system on a building. We've been doing DOAS for 50 years, pretty much the same way with DX systems. And Mojave is here to show you a different way, adding in certain components, moving other components to make it the world's most efficient DOAS product. So why are we even talking about this? Well, a couple of different things. Energy Code 90.1 is allowing us to start having less and less sensible heat in the building. So whether that's through better insulation, lower emissivity glass, LED lighting, zone cooling, the sensible loads are dropping. So air conditioning systems are not handling necessarily so much of the sensible load anymore, but also the sensible cooling equipment is becoming more efficient. But the way that we make the sensible equipment even more efficient is by taking the latent load off of it. So ventilation code 62.1, we'd all like to bring outside air into a building, right? The picture on the left, as you can see, big hole in the building that's bringing outside air in. But the problem is, especially in Georgia, and I live in Florida, is we have humidity. There's definitely other contaminant concerns as well. But the main concern is with humidity in the space. So how do we get outside air in? The picture on the right, I thought was a little bit funny because, we're trying to get fresh air into a building, but how do we treat it, right? So we have minimum outside air requirements, as everyone on this call is aware of. Air must be treated. You're going to select your DOAS for your peak condition. But again, overall, the building sensible ratio is dropping. And so latent cooling remains inefficient. Again, allowing very efficient sensible systems to become even more efficient. The way to do that is to allow a system that is very efficient to take care of the latent load in the building. So when we bring outside air into a building, again, our main concern is humidity. Don't need to really explain that to anyone on this call. Again, we're in the area of the country where that is definitely a top concern. So the indoor relative humidity range that we're looking for is really between about 30 and 60%. Anything below that, you can start promoting bacterial growth, viruses, respiratory infections, and anything above that, same exact thing. Now we're also talking about mold and bacteria. So we're really trying to keep it in that sweet spot between 30 and 60% relative. And what we're really trying to avoid is sick building syndrome. This is something that has definitely become much more common knowledge over the past decade, whether it's in classrooms or office buildings. Again, we need to bring outside air, fresh air into a building for the oxygen rate, but also we need to treat that outside air so that we're not promoting the things that we just discussed between mold, bacteria, viruses, things like that. So let me introduce you to Mojave's Arc2Dry system. This is a liquid desiccant DOAS. It's also a dehumidifier, essentially. We are manufacturing in Anderson, South Carolina. We've been manufacturing since 2022. This has been tested since 2018. The company headquarters is in Sunnyvale, California. We, fully independent tested, and we are venture backed. Again, manufacturing since 2022, and we currently have about a 10 to 13 week lead time. So 4 key components of our system. One is we're extremely energy efficient. As I mentioned before, DOAS systems are typically the largest consumers of energy on a HVAC system, and we're seeing between about 30 and 60% energy savings in the field. Secondarily, we're also seeing much lower supply air dew points than traditional DX systems, and I'll explain why that is here in a little bit, but we're seeing between about 35 and 55 degree dew points. As I go through this presentation, I want you to think of whether I'm talking about temperature control or humidity control, because for 50 years, the way that we have manipulated humidity in a building is by manipulating temperature, right? Drive the air down below the dew point, wring out the moisture in the air, use hot gas reheat to space neutral conditions, and you supply the air that you need. Mojave has independent temperature control and independent humidity control, and I'll get into that here in just a little bit. And finally, because we're so energy efficient, our payback period is very, very low. The longest I've modeled is about 18 months. We are targeting price-wise the commercial DOAS market. So your traditional, 55 degree dew point systems is what we're targeting price-wise, but we're providing a much more energy efficient system for that price. So our payback, even if we are slightly higher, 5% higher, our energy savings each month allow for very, very low payback. So what exactly is a desiccant? For any of those on the call that are unfamiliar with what a desiccant is, think anytime you've opened a pack of beef jerky, right? There's that little silica gel packet in there that is meant to absorb moisture from the air. There are solid desiccants. There are liquid desiccants. Liquid desiccants are just solid desiccant that has been put into a liquid, dissolved into a liquid. Some of the key points of desiccants are they are hygroscopic. What that word means is they have an affinity for absorbing moisture. Primarily, this is due to the vapor pressure of a desiccant itself. So just like with weather, things want to go from a high pressure to a low pressure. Same thing with vapor. The water wants to move from a high vapor pressure to a low vapor pressure. Typical atmospheric pressure is about 13 kilopascals. And lithium chloride, which is what we're using, and I'll show that here in just a minute, at about a 44% concentration is below 2 kilopascals. So again, water vapor wants to move from a high pressure to a low pressure. So what do we do about regeneration? So a desiccant will absorb moisture, and then do we just throw it away? No, we need to regenerate it. So we do that by applying heat. We do this differently than a solid desiccant system. Again, I'll show that here in just a little bit. But essentially, the takeaway is that we need a little bit of heat to evaporate that moisture from the liquid desiccant. Liquid desiccants then can thermally cycle infinitely, right? We're just talking about a desiccant, a salt, that is absorbed into a liquid. So we can manipulate the concentration of that, and the lower the concentration of that liquid desiccant, the lower the vapor pressure. The lower the vapor pressure, the more affinity it has for absorbing moisture. So if we don't want to absorb as much moisture, we want to have more liquid in the liquid desiccant, we just use less heat to evaporate that liquid out of the liquid desiccant. Eventually, this will reach equilibrium. So if we provided zero heat to our system, eventually the liquid desiccant would reach the same vapor pressure as atmosphere, and you would stop having that flow of water vapor. So again, we need to apply heat to reconcentrate that desiccant. The more we concentrate it, the lower the vapor pressure, the more we can absorb moisture in the future. Slight difference between solid desiccants and liquid desiccants. A solid desiccant uses an adsorption process, which means that it sticks, but it does not change phase. So it sticks to the solid desiccant versus a liquid desiccant, which is an absorption. We are absorbing the moisture from the air, and it is turning from a gas to a liquid. So we are going through a phase change. So, on the subject of liquid desiccants, what exactly is it? Well, it's just an industrial salt mixed with water, right? So we have different concentrations. Again, the more concentrated, the lower the vapor pressure. The lower the vapor pressure, the more affinity it has for absorbing moisture. So it is a liquid material used to absorb, not adsorb, absorb moisture from the surrounding environment. The rate of absorption is dictated by desiccant concentration and corresponding vapor pressure, which is variable. So again, as I mentioned in that previous slide, we have independent temperature and humidity control. We are manipulating the concentration of the desiccant, again, using how much heat we allow to evaporate moisture from the desiccant. So we are manipulating that, causing it to be variable, causing our vapor pressure to be variable. So what desiccant do we use? There are multiple desiccants that can be used. We use lithium chloride. There's also lithium bromide. There's several hybrids as well. The reason that we chose lithium chloride, a couple of reasons. One, it's stable, so it's non-vaporizing. It doesn't react with any airborne compounds. The only compound I know that it does interact with is hydrochloric acid. So unless that is in the airstream, you don't have anything to worry about. It is also biocidal. So it acts as a biocide to mold, bacteria, and microorganisms. And we like to, have you guys think of the Dead Sea, right? It's so salty that nothing grows in the Dead Sea. That's the same idea with our liquid desiccant. So as I'll show you here in a little bit how we interact this liquid desiccant with the air, you don't have to worry about bacteria or mold growing on the component that we use to have the two interact. So you never have to wash it down, never have to worry about those. It's also a natural antifreeze. For all those on the call, I don't think this affects any of us. I certainly know at negative 40 degrees Fahrenheit, I'm not going to be in the state of Florida anymore. But it does not start slushing until negative 40. So if there are projects that you're working on that are in extreme northern climates, again, this liquid desiccant does not start slushing until negative 40 degrees. So on the subject of liquid desiccants, again, we are manipulating the concentration. Water vapor from the surrounding atmosphere is at a higher pressure than the liquid desiccant itself. Therefore, that water vapor gets absorbed into the liquid desiccant, growing the puddle of water, essentially. So if I were to put a puddle of water of liquid desiccant on this table, over time you would see it grow as it's absorbing moisture from the air. Then we use heat to evaporate that water out, thereby reconcentrating it. So this is the cycle that I was describing, and it can cycle infinitely, right? Versus something like a solid desiccant that'll expand and contract and over time will break down. Liquid desiccants can thermally cycle infinitely. So you could even take a unit today, and let's say it lasts 15 years, whatever the lifespan is. You install a new unit to replace it. You could actually remove the liquid desiccant from the first unit, put it into the second unit, and continue to operate the system. As you'll see as we get further down in this discussion, they never need to top this stuff off. It's very, very salty water. So if it touches your skin, certainly it's something that you would prefer to wash off. But it is non-toxic. I did forget to mention that as well. I have had the unfortunate pleasure of getting some on my finger and then touching my lip before, and I just needed a little bit of chapstick, and I was perfectly fine. So again, it's not toxic. So maintenance staff doesn't have to worry about the getting it on their skin, other than the fact that it's very, very salty. So wash it off with some water. Really quick, I want to compare solid and liquid desiccants. They both have their advantages and disadvantages. But some of the factors that I want to discuss are more moisture absorption capacity. A solid desiccant, this is more fixed. It's based on the wheel size. Whereas I mentioned before, liquid desiccants, it's variable. It depends on the concentration of the liquid desiccant itself. The lifetime, as I mentioned before, liquid desiccants, we can cycle infinitely, versus solid desiccants do have a limited lifespan. Dewpoint and temperature control. And a solid desiccant, this is static. The media has a minimum regeneration temperature. So we do have to see very high temperatures for those. Versus a liquid desiccant where it's flexible, again, based on that concentration, and we can regenerate with condenser heat. And I'll show you that in a little bit. We need far less heat to evaporate the moisture out of these liquid desiccants than you would for a solid desiccant. There's also no parasitic heat crossover versus a solid desiccant wheel. Some of the IAQ benefits, again, because this is a very salty solution, it is biocidal. There's no cross-contamination. Maintenance-wise, you'll see at the very end of this presentation what the maintenance of these systems is, and it is extremely minimal. As I mentioned before, you never need to top these systems off. The liquid desiccant doesn't leave the system itself. We do have a little tea strainer that you should check out every time you change the filter, but I'll show you that here in a little bit. Dewpoint capabilities. Solid desiccants do have exceptional dewpoint capabilities, very, very low. Liquid desiccants can get down to about 35 degrees on the bottom end, which is far better than traditional DX with hot gas reheat. But again, we really can't go below about 35 degree dew point. Cost-wise, as I mentioned before, liquid desiccants, especially Mojave, are really targeting the commercial DOAS market. We're really not trying to necessarily play in the same space as a solid desiccant, extreme low dew point type of system. They absolutely have their applications, but that does come at a cost premium. So, what are the two main benefits of Mojave's system? There's low dew point, as I mentioned previously, and there's also very high efficiency. So, I want to talk about for a minute here why that happens. So, if you look at this beautiful diagram that I came up with, we have water vapor that is in the air. Okay, air molecules surrounded by water. Now, there's only so much water that can be held in the air at a certain temperature. As we increase our temperature, we spread out those air molecules, allowing more space, therefore allowing more water to be absorbed into the air. Inversely, as we decrease our temperature, we compress those air molecules and we start condensing. And once we reach the dew point, that is when we start condensing moisture out of the air, right? We start forcing those water droplets out of the air. The lower temperature you get, the more energy it takes. So instead, if we were to put in something like a liquid desiccant that absorbs water without necessarily having to manipulate temperature, we can absorb more moisture at a higher temperature. And I'll show you that psychrometrically here in a little bit. But again, this is allowing for essentially absorbing the moisture out of the air separate from just temperature control. And if we mix the two, if we continue to drive that temperature very, very low and add in liquid desiccant, now is when we can really start wringing a lot of moisture out of the environment. Now is when we can start getting it to much lower dew points. Uh, so again, we don't need necessarily as low of temperature to get to normal supply air dew points, but to get to very low dew points, obviously we're going to have to drive the temperature down farther. So really quick, I want to recap on the low dew point of liquid desiccants. Vapor compression really can get down to about 46 degrees. Chilled water can go down to about 42. You really have to start looking at 35%, at glycol at those levels. And then liquid desiccants can get down to about 35-degree dew points, and below that is solid desiccants. So this is really your spread of systems. Again, we are targeting the traditional DOAS market. So pricing wise, we are absolutely in play for 46 plus degree dew points. We are a low dew point capable machine. We are not a low dew point only machine. So let's talk about the other benefit of Mojave's liquid desiccant system, and that is ultra high efficiency. So as I mentioned before, if we don't have to drive the temperature down as far to remove as much moisture, we are saving energy. Every line of enthalpy on the psychrometric chart that you cross over is exponentially more energy intensive. So to go from 60 to 59 takes less energy, less cost than to go from 59 to 58, right? So every line you cross over is exponentially more energy intensive. So the fewer lines of enthalpy we have to cross, the better. Really quick, before we look at the psychrometric chart, I want to talk about ISMRE. For those that are unaware, MRE is moisture removal efficiency. ISMRE is very similar to, sorry, I'm completely blanking on anyway, ISMRE is integrated seasonal moisture removal efficiency. IEER is what I was trying to compare it to. I apologize. So this is a ratio of the moisture removed from entering air volume to the total power input at the given set of rating conditions expressed in pounds of moisture per kilowatt hour. ISMRE2 is where we currently are, a slightly different ratio. So we're looking at about 12% of A, 28% at B condition, 36% at C condition, and 24% at D condition. As you can see over here, A, B, C, D, what the conditions are. The most energy efficient condition is 70-66. However, the highest moisture removal capability is at 80-73. So again, we're going to take a blend or a ratio of these to come up with an ISMRE2 value. Now, not every manufacturer of HVAC equipment has to have an ISMRE2 value. However, for manufacturers that are primarily or solely 100% outside air machines, they do have to provide an ISMRE2 value. We do have a return air knockout, so we are not 100% only outside air. We do have the capability to have mixed return. However, we are a primarily 100% outside air DOAS machine, and so we do list our ISMRE2 value. The federal minimum for ISMRE2 values for air-cooled without an ERV is 3.8 pounds per kilowatt hour. For air-cooled with an ERV, it is 5 pounds per kilowatt hour. Now, I will preface this by saying the number you're about to see from Mojave is without an ERV. We do have the ability to put an ERV on these systems. If it's required by code, by local code, certainly you can put an ERV on these systems. However, um, I would I would dare to say it does not affect the rating very much. So again, federal minimum without an ERV is 3.8, with an ERV is 5. Mojave is 10.8 without an ERV. So we are more than twice as energy efficient as the federal minimum with an ERV, and that is without us having an ERV. So when I say Mojave is the most energy efficient DOAS system on the market, this is proving it right here, the ISMRE2 value. So again, if you are looking at a project and would like to compare apples to apples, certainly you need to look at the ISMRE2 value, not necessarily the IEER values. So how do we do this, right? This sounds great. We're very efficient. We can do low dew points, but how do we do it? So obviously here's the psych chart, and what you're seeing here are the typical traditional DOAS with hot gas reheat, right? We have a starting point of outside air. We're going to cool down to the saturation curve. We're going to follow that curve all the way down to, let's just say, 55 degrees, and then we're going to use hot gas reheat to reheat it to space neutral condition. We're essentially overshooting the wet bulb desired end condition and then reheating to the desired end condition. So think of this as essentially you are overshooting your target and then having to reheat to get to your target, right? So it takes a lot of energy. So the way that we could conserve energy is instead of driving down to 55, what if we went down to 61, hypothetically? So if we drive down to 61 degrees and then reheat it with hot gas reheat, we're not going to hit our space condition. However, if we allow liquid desiccant to take over the dehumidification process, we can follow this line of enthalpy down to our space condition. The more of this little triangle at the bottom that you can cut off, the more energy you save. Because again, as I mentioned, every line of enthalpy you cross over is exponentially more intensive, costs more money. So on a peak load day, we are going to use we do have a DX system. We're going to drive down to, again, 60, 61 degrees, and then we're going to allow the liquid desiccant to take over the dehumidification process. Now, for those of you that are very in tune with scientific terminology, this is an isenthalpic process. What that means is for every bit of latent, let me scroll here. So for every bit of latent that we are picking up, we are giving off sensible. So we don't have hot gas reheat because we don't need it. We do pick up about 10 to 12 degree delta off of our pad that I'll show here in a little bit. So again, we're gonna cool down to about 60, 61 degrees, allow that isenthalpic process through dehumidification to take over, and we're going to follow that line of enthalpy down to our space conditions. Now, when you are dehumidifying, you are heating. It's the exact opposite of a swamp cooler, right? So again, when we are going down and to the right, we are dehumidifying and we are heating. When you're going up and to the left, for instance, you are humidifying and you are cooling. So it's exact opposite process. In part load days, we can see this even more. So up above, we have the traditional DX system in design day, same thing I just went through. And in part load day, sometimes we have insufficient load to reheat to target conditions. So we can see not reheating to space neutral conditions, providing space temperatures that are too low, and also the compressor kind of going on and off, obviously, throughout the day. Mojave's arc to dry system. Again, on design day, we're going to have a little bit of that triangle cut off at the bottom. Let's just say hypothetically 30%. The lowest that I've modeled is about 25% at a 0.4% dehumidification day. So even at peak conditions, we are still about 25% more energy efficient. And then obviously during part load days, we get even more efficient than that. So the more of that triangle we can cut off, the less DX cooling that we need to use to get to our target supply air condition, the more energy that we save. So just to show that on a chart, we do have remote telemetry in all of these units. And so this is what the chart looks like if you would like to, log in and see your unit, or if, the building owner would like to log in and see their unit. We do have this on every single unit from the factory, so that, we can monitor it. We obviously get alarms if anything goes wrong. But what this is showing is the outside air dry bulb and supply air dry bulb. It's really only about a 2 degree delta, so it's a part load day. Not very hot outside, but it is humid. And so the outside air dew point and the supply air dew point has about a 12 degree delta. During this condition, a traditional hot gas reheat DOAS unit would struggle to maintain the supply air dew point conditions versus the Mojave Arctic-Dry system. As you can see, that blue line all throughout the day, that's over about a 12-hour period, fluctuated within about plus or minus 1 degree of the set point, the dew point set point. All right, so switching gears a little bit, as I mentioned before, what we are doing is we are absorbing moisture from the environment, right? So we have water in the air, we are absorbing it into the liquid desiccant itself. How do we do that? Well, we have a pad. So this is the absorber pad. The desorber pad is very similar. It's a little bit bigger. But essentially what this is doing is there is concentrated liquid desiccant flowing through a header at the top of this pad. It is then permeating or penetrating this pad. The air is flowing through these channels. The air is directly touching the liquid desiccant. So there are no heat exchangers or anything like that. The air is directly touching the liquid desiccant, which again has permeated this pad. As the concentrated liquid desiccant flows down, it is picking up moisture from the environment. It is becoming dilute. We then have a tank at the bottom of this that catches that diluted desiccant, and we send it to the other side. Here, I'll show you in just a minute. And we're doing the exact opposite process on the other side. So the desorber pad, where we are evaporating moisture out of the system, you have diluted desiccant flow from the top down to the bottom, and it is reconcentrating. But again, this is the pad. This is what you don't ever need to wash. You don't need to replace. It lasts the lifetime of the unit. And the air is directly touching the liquid desiccant as it flows through this pad. As I mentioned before, this is an isenthalpic process. So as the air flows through, it is picking up moisture, it is dehumidifying, and it is heating. Again, as we are absorbing latent heat, we are giving off sensible. It's about a 10 degree delta over that pad. And this is just showing the concentration the vapor pressure at different concentrations. The more concentrated we get, the lower the vapor pressure. The lower the vapor pressure, the more affinity we have for absorbing moisture. So at 44% in solution, we're at about 1.47 kilopascals. And at 35% solution, we're about 2.2. Again, atmospheric conditions are much higher than this. So the more concentrated that we get through adding heat on the regeneration side, the more moisture we can absorb. Speaking of regeneration, again, we need heat to evaporate the moisture out of this pad. Again, it's the pad that you see on the right. It's a little bit bigger than the absorber pad. This is called the desorber pad, and it's on the other side of the unit. But essentially what we're doing is we are using heat to evaporate moisture out of this solution. Right, so we have diluted desiccant flowing down from the top to the bottom, and we are reconcentrating it as it flows down by allowing that heat to evaporate moisture out of the solution. How do we do that? So we don't have what you would consider necessarily a hot gas reheat coil. So I made a little diagram here to really show what you traditionally have with the reheat coil. You have your evaporator coil, the air comes in, cools down, get below the dew point, you reheat space neutral condition, and you supply it to the air. What we've done is we've moved that reheat coil. So instead of being behind the evaporator coil, it is now in its own air tunnel. So same idea in terms of how the hot gas is flowing and everything else. But instead of having the reheat coil behind the evaporator coil, we now have it in its own air tunnel. That is the regeneration air tunnel. Then what we've done is we've put these two pads in here. One is the absorber pad, which again is taking concentrated desiccant, flowing through it. It is picking up moisture, becoming more dilute. It is then sending that diluted desiccant over to the desorber pad, which is sending diluted desiccant from the top, gravity fed through the pad. It is reconcentrating it based on the heat provided by our hot gas reheat coil. So what does this look like in real life? Here's a nice diagram of our unit. As you can see, there's a wall right down the middle of the unit. These two air paths do not share, or these two paths do not share any air whatsoever. There's no, parasitic heat transfer or anything like that, like you would have in a solid desiccant wheel. As you can see on the far left, at the bottom, we have outside air coming in. We do have that return air inlet, if you would like to use some return air. But outside air is coming in. First thing it's going to do is pass through our filter bank. This is a 2 and a 4-inch filter bank, MERV 8, MERV 13. It's then going to pass through a 4-row coil. We don't have 6-row coils or 5-row coils. We're using a 4-row coil because we're not getting the vast majority of our dehumidification through our cooling coil, but we are getting some. So there is a little drain you'll see down there at the bottom of the coil. So the air passes through the filter bank, passes through the coil. Next, it's going to see the absorbing pad. Again, concentrated desiccant is flowing from the top of the pad down. It's picking up moisture and it's diluting that concentration as it goes down. The air is then going to pass through the winter heating module. So this is gas, electric, hydronic, or heat pump. So if you do need to reheat more than the pad can provide, we can utilize that winter heating module to reheat to whatever space condition you're looking for. But that is primarily a winter heating module. And then you're going to pass through the ECM supply fan, 3 inches of static, and we have side and down discharge. On the other side of that wall is our regen side. So we're going to take outside air, we're going to pass it through our reheat coil, then we're going to send that hot air over the desorber pad. And what the desorber pad is for is, again, we're taking that diluted desiccant, it's flowing down through that pad, we're providing heat across that pad, essentially acting almost as a swamp cooler, where you are providing more humid and cooler air on the other side of that pad, but we're evaporating that moisture from the solution itself. The more heat through that hot gas reheat coil that we provide, the more concentrated we can get the desiccant. So I said almost in the beginning of this presentation, there's independent temperature and humidity control. So we are not relying on manipulating temperature to control humidity. We can have cold supply air temperatures and not provide as much dehumidification if we don't want to, or we can have warmer but drier conditions. And again, that is through manipulating how much heat goes across this desorber pad, which manipulates the concentration of the desiccant. As I've said several times, the more concentrated the desiccant, the lower the vapor pressure, the higher the affinity for absorbing moisture. Again, independent temperature and humidity control. For those of you that like diagrams more like this, same exact thing. We're bringing the outside air in at the top on the left through the evaporator coil. Our compressor, we have a 3-way modulating valve. So the hot gas off the compressor can either go through our traditional condenser or it can be rerouted to that regeneration or the hot gas reheat coil. Again, this valve determines how much of that hot gas we send over the reheat coil, which determines how hot that temperature is, which determines how much moisture we can evaporate from the solution, which again determines the concentration. So on days where we need more dehumidification, we're going to provide more hot gas to that reheat coil, therefore providing hotter temperatures, hotter air temperatures to evaporate more of the moisture from the liquid desiccant. On days where we don't have nearly as much of a dehumidification need, we're going to send the vast majority through our traditional condenser. What I also want to note on this is what the liquid desiccant system is. So it's really at its core, it's 2 pads, 2 pumps, and some sensors. So as you see here, we have our absorber, we have our desorber. We do have 2 fractional horsepower pumps. These are, off-the-shelf pumps. You can't get them at Home Depot because obviously liquid desiccant is a very corrosive material, so it needs to have a certain type of pump. But these are not proprietary to Mojave. You can certainly order these online or wherever you'd like to. And so we do have, again, 2 pads, 2 pumps, and then some sensors. We have very, very sensitive leak detection systems. And underneath the the entire liquid desiccant system is a plastic tray. So underneath the absorber is a plastic tray, underneath the desorber is a plastic tray. If anything catastrophic were to ever happen, it's PVC piping. Let's just say a maintenance person goes in and accidentally trips, breaks one of the PVC pipes. That liquid desiccant would then flow into that plastic tray where we have leak detection systems. If those leak detection systems are tripped, it will turn off the liquid desiccant system. So it will stop those pumps. It will not turn off the overall unit itself. So you're still going to be providing some dehumidification through the DX side. But again, the liquid desiccant system would be turned off. Alarms would be going off. Everyone that wants an alarm would be getting an alarm. Again, because there's catastrophic failure or there's a leak detected in the system itself. So one of the main questions that I always get, and it's a very valid question, is what about carryover? What I mean by carryover is, as I mentioned before, the air is directly touching the liquid desiccant. Liquid desiccant is very corrosive. Things that are metal don't like corrosive liquid. So the last thing we want to do is suck any of this liquid desiccant off of the pad, right? Because everything downstream is metal between our unit itself, the ductwork, the grills, everything. If this solution touches metal, it's corrosive. So we have tested this. Like I said, we've been testing since 2018, but we have tested this multiple times. And we are actually very close to releasing a new test that is even more finite than this. But essentially what we're showing is the absorber mass accumulation data and the desorber mass accumulation data. So we set up these absorbers through the absorber and the desorber with a tunnel with filters to act like, it would normally operate in the field. And then we have, the ability to capture how much of this carryover happens. And as you can see here, both the absorber and the desorber exhibited less than 1 part per billion accumulation. So 99.99% confidence. We have now tested down to parts per trillion, and we are at about 70 parts per trillion carryover. So again, effectively zero. So what we like to call this is an engineered closed loop system. It is open loop in terms of, again, the air does directly touch the liquid desiccant, but we're really, really good at keeping that liquid desiccant on the pad and not sucking any of it downstream. So we call it an engineered closed loop system. We have a 3x safety factor on the face velocity. So what we're limited to with our airflows is based on the size of the pad itself. There's only so much of this liquid desiccant the pad can hold, right? And if we're pulling air through the system too quickly, we're going to increase our potential of carryover. So we keep our face velocity very, very low. And there are some other geometry features of the pad itself that provide the ability to keep the liquid desiccant on the pad and in the system and not have any of this carryover. And finally, on the right, what you see is we did have in the field itself, there's another rep in another state that had one of these systems in their building for 2.5 years and put a copper thin film corrosive strip on there. And after 2.5 years, it looked pristine. So again, we can conclude that our supply air presents an ISO C1 environment with 99.999% confidence. So for those that are concerned about carryover, I certainly understand the concern. As I mentioned in the very beginning of this presentation, liquid desiccant is not new. It's been on the industrial side for a long time. There have been other iterations of trying to use liquid desiccants in commercial applications. And sometimes design-wise, this has been met with some limitations and have led to some corrosive environments. And, again, making sure that this desiccant doesn't touch metal is the primary concern. Now, I will say over the next probably 5 years, we are going to see more manufacturers utilizing liquid desiccant. The number one factor that I would caution all of you on this call to pay attention to is what is the carryover? How good are you at keeping that liquid desiccant from touching metal? Because again, the moment it starts touching metal, you're going to have corrosive environment, and it's not going to go well for the system itself. We've been testing this for a long time. We are extremely confident, and we can prove the fact that we have effectively zero carryover. All right, so enough of chemistry lab. Let's talk about what these units actually look like. We have two cabinets. We have an A cabinet and a B cabinet. These are package systems. They can go on the roof. They can go on a pad on the ground. A cabinet is 1,000 to 4,000 CFM, and B cabinet is 3,000 to 8,000 CFM. That is an intentional kind of gray area between 3 and 4,000 CFM. Some environments, like the North, you can get 4,000 CFM out of an A cabinet. Environments like the South, where we have a higher humidity concern, you might not be able to get 4,000 CFM out of the A cabinet. So you might have to switch to the B cabinet. So that's why there's that kind of carryover area. These are slightly longer than a comparable DOAS system with hot gas reheat, not by much, but they are a little bit heavier. They're about 10%, maybe 15% additional weight. So if it's going on a roof, certainly something to think about structurally. If it's going on the ground, not quite so much of a concern about weight, but again, it could be a little bit longer than you might traditionally be accustomed to. And the reason for that is we need the space for the absorber and the desorber pad. Again, real life example here on the A cabinet, you can see the outside air hood is that thing on the far right. That's the outside air tunnel on the other side of the unit. And what you're seeing on this side of the unit is that regeneration tunnel where you have outside air come in through that smaller hood that's closest to us, pass through the hot gas reheat coil, heating up, and then it's going to go across the desorber pad where that Mojave logo is. The desorber pad is behind that, and it's going to flow out of the top of the unit itself. Some of the specifications really quick, as I mentioned in the beginning of this presentation, really not getting too heavy into the specs or the customizable features of this. It was really meant more to show you guys the technology and how it's applied. Our standard construction, again, 100% outside air or mixed or recirc capable. 2-inch double wall construction, foam injected panels, inverter driven compressor, ECM supply fan. We do have that remote telemetry I mentioned before on every single unit. We do have the capability for BACnet and Modbus. Every one of our access panels is fully removable. We have 4 hinges on each access panel, so that makes it very nice for maintenance. And we do have washable T-strainers. So I mentioned before, the A cab is from 1,000 to 4,000 CFM. B cabinet is 3,000 to 8,000. As you can see, at the highest, our moisture removal capabilities are 380 pounds per hour. It's a lot of water. ISMREs up to 10.8. And weight, again, this might be a little bit higher than you're accustomed to. Obviously, this has some variable, components or factors as well, but we are a little bit heavier than your traditional DX system. And some of the configurable features, as I mentioned before, the winter heating module can be gas, electric, hydronic, or heat pump. We do have the capability to have an ERV if you need it or if you'd like it. And then we have your typical, return air openings and dampers, inlet openings and dampers. We do have salt spray coating for those of you on the coast. I know that's very popular where I live in Jacksonville, and we do have, and that can be interior and exterior or both. And we do have coil coating options as well. Condenser hail guard, I would recommend this on pretty much every single project. And then we do have certified storm louvers as well. All right, so let's talk about really what makes this different from a maintenance perspective and a warranty perspective. So we do have a 2-year parts warranty, 5-year compressor warranty. We also offer a 5-year desiccant system warranty. Everything that is associated with the liquid desiccant system, again, has a 5-year warranty. That'd be the pads, the pumps, the sensors, anything like that. As I mentioned before, the pads never have to be replaced, never have to be washed down or anything like that. But within 5 years, if a pump were to go out or if a sensor were to go out, it is covered by that warranty. Startup is performed by Mojave Techs. So our national service manager lives down in Fort Myers. He and his team do go to every single project and perform the startup right now. We do also factory run test for about 2 hours prior to shipment. This is a little bit unique because what we do is we actually try to imitate the environment that it's going to as best we can. So again, manufacturing is in Anderson, South Carolina. I did forget to mention we're about 76% domestically sourced. We're not getting these boxes from overseas and putting some components in there and trying to resell it to you guys. We are physically from the ground up building these units. I know that because I've done it there in the factory. So we try to manipulate the environment in the factory or in a small part of the factory to replicate the environment that's going to. And we factory run test these units for about 2 hours each. And the reason for that is so we can have that liquid desiccant flowing through the system and we can know what the volume of desiccant needs to be. Um, so when the unit is shipped, we remove that liquid desiccant from the system, put it in 5-gallon buckets, ship those buckets with the unit because the last thing you want to do is ship liquid desiccant in the system because it'll slosh all around. When it gets to the job site, it's installed. The buckets that come with the unit is the liquid desiccant it was tested with in the factory at the correct concentration and at the correct volume. And we do have a factory trained technician program that we launched this year. It's been very effective so far. But again, you guys have the benefit not only of having obviously the entire support of Holden, but our national service manager is close by, and our manufacturing facility is right across the border in South Carolina. So not concerned about any issues that might arise in the territory. We certainly have the coverage for it. So what are some of the maintenance features? Again, main question that I'm asked. As I mentioned before, we have these double hinge access doors, so they open from both sides, or you can just take the whole panel off. Makes maintenance very simple. This is toolless removal, toolless filter access. You don't have to worry about losing a tool to open up the panel. And then finally, we have these mesh desiccant T strainers. So there's one in front of each pump. So as I mentioned before, there's two pumps. So there's two T strainers. When you open up the access panel, you'll see both of them right in front of you. This is a picture of what one of them looks like over here on the right. You just unscrew that if there's any contaminants in the system. So outside air is going to flow in. It's going to pass through a MERV 8 and a MERV 13 filter. If contaminants get through those two filters, you're going to have the DX cooling coil. If the contaminants get past the DX cooling coil, then it could theoretically get on the pad. We do have several projects that are installed in very contaminated environments, if you will, like on the ground where people are mowing grass and they have leaves and things like that. So far, we have not had an issue with a lot of particles getting onto the pad itself. But the channels in the pad go down at an angle like this. So as that liquid desiccant is flowing down, it's kind of filtering to the outside of the pad. So that will allow those contaminants to fall down into that tank at the bottom of the pad itself. And then these T strainers, again, before each pump, are going to filter any particles out. What we recommend is when you change your filters, fingers crossed, every 3 months, have the maintenance staff check these T strainers as well. If there are particles in the T strainer, you just unscrew it, toss it out, not the T strainer, toss the contaminants out, and then wash it, rinse it with a bottle of water, stick the T strainer back on there. The system will adjust to if any of that salt is lost or anything. It's not going to be because, again, the volume in these T strainers is very low. But that is the only maintenance for the liquid desiccant system itself. Pads never have to be washed, never have to be replaced. The pumps, if they were to go out, they would need to obviously be replaced. But the only preventative maintenance really are these T strainers to ensure that those pumps don't get clogged up. So your normal DX system maintenance is obviously very applicable between filter changes, coil cleanings, drain cleanings, inspections, things like that. But again, on the liquid desiccant side, the only thing that we really need to be concerned about are those T strainers. Just check those. Again, if they're contaminated, we can rinse them out. And that concludes this presentation of Mojave's Arc2Dry system. Again, my name is Brian Schmidt. I'm the regional sales manager. If anyone would like to get in touch with me, here's my contact information. But obviously, Holden Associates is our rep in the state of Georgia. They're a fantastic partner. So reach out to them first. But if you have any particular questions that I might not get to today, feel free to reach out. And Tracy, I will hand it back to you.